Okay, let's start lesson 12.2b. So we're getting near the end here. This is about the relationship between two categorical variables. So the question is, are people who are prone to anger more likely to develop heart disease? My guess is this could be true. An observational study followed a random sample of over 8,000 people with normal blood pressure for about 4 years. Each person took the Spielberger trait anger scale test. Researchers also recorded whether each individual developed coronary heart disease called CHD. Okay, so how many developed it? It looks like there were more folks with CHD when you had higher anger levels. So it seems the data seems to support that. Just looking at the bar charts there. Does this provide convincing evidence? So let's do a test here. So what's the null? There's no association between anger level and heart disease. There's nothing going on here. There's no association. What's the alternate? There is an association between those two variables. So you're taking kind of one sample, but you're looking at it from, well, do these two variables kind of associate with each other? You could also say it this way, and this is the equivalent way of saying it. So you could say, some people always just use the word independent there, that anger and heart disease are independent. They have no effect on each other. We've used that term earlier in the year for independence doesn't have an effect on each other, or they are not independent. They do have an effect. There is an association. So really, it doesn't matter your preference. It could be fine there. So let's do expected count. So similar like we did, we actually did this with the last lesson. It's the same formula, right? So it's the row total, which is 190, times the column total, which is 3,110, divided by the grand total, 8,474. If you do that, you should get the answer. That's the formula for expected counts. Again, you don't have to calculate them by hand. Usually we can type the matrix in our calculator, do the test, and kind of go from there. So let's do that with this one. So let's type the matrix in. So if you take away the total columns and rows, it looks like a 2 by 3 matrix. So I'm going to hit, I'm going to do it a different way. So if you go to menu, matrix, and create a matrix, you can choose, we think it's going to be a 2 by 3. I hit tab to go to the next cell. It's easier. There it is. Okay, 53, tab, 110, tab, 7. Yeah. 1 and 606. Oops. Okay, so we're going to store that. So control variable is store. You put a little arrow there, and we're going to call this anger. And now I'm going to run my test. So menu 6.7 is test, and it's a chi-squared two-way test. Chi-squared two-way test. You're going to choose your anger in that case. And if you want to see the expected matrix, hit the variable, choose expect matrix, and there it is. So it's got a lot of data that I might need there. It's got all the expected counts just like we see in the bottom right-hand side. So you can just let your calculator do that for you if you want. So now when we check the conditions, I almost have to do that before checking the conditions. Is it a random sample? I believe it was. Let's go back and just look at this. It might be worthwhile to look at it for a reason I'll talk about in a minute. So an observational study followed a random sample of 8474. So it was indeed a random sample. Less than 10%. So this 8,400 is less than 10% of all the folks who might develop heart disease. It's pretty much out of everybody. Yeah, that's way less than 10%. And then all the expected counts. So you look at this, essentially your calculator here, right? So you're looking at those values right there. In blue, all those are bigger than or equal to 5, so we're good on that end. So it does seem to pass that test. Conditions, make sure to write all expected counts are at least 5. Again, we're going to use the same chi-squared. Degrees of freedom is number of rows times number of columns. Number of rows minus 1 times number of columns minus 1. So you multiply those two things together. Chapter 1, you read about a random sample of winter visitors to Yellowstone National Park. Each of the 1,500 visitors was asked 2 questions. Do you belong to an environmental club? And what is your experience with the snowmobile? Own, rent, or never used? So they filled out the table using the results of this observational study. So just one random sample. They're really collecting 2 variables, though. That's usually kind of a hint that this might be a test for independence and maybe not a test for homogeneity. So that's just kind of a hint right there that you might go, this might be asking about, again, the association between these 2 variables. Do these data provide convincing evidence of an association between environmental club status and type of snowmobile used in the winter? Okay, so the null is nothing's unusual, right? So we don't think there is an association. There is no association between snowmobile use and whether you're in the environmental club or not. So there's no association. The alternate is there is an association. So this is clearly a chi-square test for independence. You could also say, if you wanted to, you could talk about it being independent. These 2 things, these 2 variables are independent, would be the null. There's no association, there is an association. Okay, what's the next step? So you want to look at what's the name of the test? It's a chi-squared test for independence. What are the conditions? The random sample, yes, it was a random sample of folks. That's what it says, of winter season. And is it less than 10%? So we think 1,500 is less than 10% of all the visitors to the park. And large counts are all expected counts. So what you want to do there is, type in the data, right? So this is going to be 3 by 2. So if you go to the template here, 3 by 2, say OK. Let's type in the data. I like hitting tab. Okay, so now we're going to hit control variable for stow, and we'll store that as snow. Okay, so let's do our test in our calculator. Menu 6, 7 is tests, and this is a chi-squared 2-way test. Choose your matrix. It's called snow, and there it is. If you want the expected matrix, go variable, expect matrix, and you've got those numbers as well. So you want to, again, name the test, chi-squared test for independence. Check the conditions. We've done that. So now you do the do part. So you really want to see a few of the fractions there. So what you might be expected to show is after you write down all your expected values there, I write them right in the cell. So I write right next to never used is 445. That's the observed. So I would put flash and put 525.7 in that same box if I were you. So they want to see the first 2, maybe even the last one as well, typically for work, for chi-squared. So you can see they took the observed, 445, minus the expected, 441. I'm sorry. That looks different than theirs. I wonder why. We look back and see the same numbers. They did not. What's my expected matrix here? What's my matrix called snow? 445, 212, 497, 77, 279. It would help if I put this in, right? So 16, 279, 16, and we're going to store that as snow. Now we're going to redo the test for snow. Show the expected value matrix. So you can, you guys just type the numbers. Sometimes those pesky little totals get in the way of typing in the numbers correct. So now if we look at it, 445 minus 525.7, yes, that makes sense. So I just wanted to make sure I had it right. Degrees of freedom is 2, and it is because there's 3 rows minus 1, 2 columns minus 1 is 2 times 1, which is 2. The p-value seems to be very small. 4.82 times 10 to the negative 26, so it's very close to 0, so we are going to reject here. Because the p-value is approximately 0, it's fine to say it's very close to it. We reject the null. We have convincing evidence of an association between environmental club status and type of snowmobile used in the population of winter visitors to Yellowstone National Park. When the p-value is small, just be aware of this. Like it might say 4.82, but then it has e to the negative power there. Like it might show scientific notation like this one does, right? You can see in the calculator, it says that. That means 4.82146 times 10 to the power of negative 26. That's the same thing, right? That's scientific notation in the calculator. So if you haven't seen that before, just because it says 4, you'd be expecting like, wait a second, probabilities between 0 and 1, 4 is impossible, but 4 to the times 10 to the negative 26 is certainly possible. So that's something to keep in mind. Use these wisely. So they're very similar. How the data were collected or produced is really the thing here. So if the data comes from 2 or more independent random samples, then it's going to be a test for sameness or homogeneity. If the data comes from a single random sample where they're collecting data on 2 different categorical variables, that's going to be chi-squared test for independence. So that's kind of the higher end way of, sometimes it's obvious in the way they ask the question, but sometimes it's not obvious. So this one, are men and women equally likely to suffer lingering fear from watching scary movies as children? Researchers asked a random sample of 117 college students to write a narrative accounts of their exposure to scary movies before the age of 13. More than 1/4 of students said that some of their fright symptoms are still present when they are awake. The following, wow, I don't think we should show scary movies to kids under 13, probably. I know my kid was scared of some Harry Potter stuff when he was that age. They didn't want to go on the Harry Potter ride. I was like, you got to go on the Harry Potter ride. So I probably exposed him to too much. The following table breaks down these results by gender. Okay, so here they are. Got all the data. Assuming the conditions for performing inference are met, Minitab output is shown. Should a chi-square test for independence or homogeneity be used in this setting? So is it about homogeneity, like same and difference, or is it about the other one was independence? So like, is there association between the 2 variables? So what is really the question that's asking here? How is the data collected? These are the kinds of things we're thinking about. So we talked to 117 college students. So they asked about, they said, are you male or female, and do you have fright symptoms or not? So there's two categorical variables, but only one sample was taken. So because of that, I think it's got to be a chi-square test for independence, because the data are produced using a single random sample of college students and then classified according to 2 variables. So that's what this kind of test is, whereas the chi-square test for homogeneity requires independent random samples from each population. We could just go on and state, so if it is association or independence, then there is no association, or these 2 variables are independent of each other. The alternate is there is an association, or these variables are not independent of each other. Which cell contributes the most to the chi-squared statistic? So to answer that one, you might want to do the test in your calculator. So let's go ahead and do that. So this is going to be, I guess, just a 2x2, right? So you can actually just choose 2x2 right here. So I hope I can type it in correctly this way: 7, 29, 31, and 50. So we're going to store that as scary. And I'm going to do the test. The menu 6, 7, I think it was 2-way test. And we're going to choose scary. So we get that. And let's look at the expected matrix in case we need it. Okay. So let's go back to the question now. Part B. Part C. Which cell contributes the most? Oh, I didn't look at the one I need. I'd go very comp matrix. So those are the contributors. And so it looks like the top left was which cell? That was the males who said yes. So males who were scared is the biggest contributor to, how did they say it? Which cell contributes the most to the chi-squared test statistic? And men who admit to have fright symptoms account for the largest. Far fewer men in the sample admitted to lingering fright symptoms than we would have expected if the null was true. That's the difference there. Interpret the p-value. This is always tough. So assuming the null is true, what's probably you get an answer as extreme as that or more extreme. So if there is no association, that's the null is true, between gender and whether or not college have lingering fright symptoms, there is a 0.045 probability of obtaining association as strong or stronger than the one that was observed in the random sample of that many students. And finally, interpret the p-value. Because the p-value is less than the alpha level, or greater than the alpha level, sorry, we fail to reject. We do not have evidence that there is an association between gender, whether or not students have lingering fright symptoms. So it seems like maybe the thing is possibly that maybe before age 13 might have something to do with it, but gender doesn't seem to play a role here. So that's the kinds of questions you can answer about this. Hope you enjoyed the lesson.